Today we're going to cover natural logs and the natural base e. So if you remember from before, we had several important formulas. One of them was the compound interest formula. Another one was the continuously compound interest. A is equal to principal e to the power of RT. So today we're going to talk more about that e. We also have the half-life formula, which you need to know, also has the e in it. So what is e? E is a constant number, 2.718 ... It keeps going. Think of pi, but it's a different number than pi. So we'll never actually use the 2.7. We'll always plug this into a calculator. If we were to graph this, it looks like an exponential equation. However, the y-intercept is at c. The opposite of e is ln. Ln stands for natural log. What that is, it's simply a log with the base of e. So e and ln are opposites or inverses. When we're solving and using the natural log, we use the same rules as we did for regular logs. Nothing has changed except for we write ln instead of log. So we remember from logs that if we had log base 10 of 10, they simply cancel out. Same thing with the natural log and the e. If I have a natural log of e, they simply cancel out, and we're left with whatever was there. So my answer here would be x minus y. We remember from logs that if you had 10 to the power of log base 10, then those just cancel out. Same thing here. I have e to the power of natural log. They cancel out, leaving me with 2x. So if you remember from regular logs, if I had 3 log of x, the 3 can become an exponent of the x, which would give me log x cubed. Same thing with the e's in the natural logs. I can take this 3 and put it on top of the x. What that's going to give me is e to the power of natural log x cubed, and then I know that e to the power of natural log cancels out, giving me an answer of x cubed. Let's take this one step farther. They ask, what is 3 natural log of 5 plus natural log of x written as a single logarithm? If we remember from regular logs, I have log of m plus log of n. What that's going to do is multiply my m times n to give me log of mn. Same thing is true with the natural logs. If I'm adding the natural logs, what I'm going to do is be multiplying the numbers inside. At the same time, I need to take that 3 and put it on top of the 5. What that's going to give me, natural log of 5 cubed plus natural log of x, and then I'm going to multiply those, which gives me natural log 5 cubed x. Now, because it's only 5 cubed, we should be able to multiply that out in head, which gives me an answer of natural log of 125x. When we start solving natural log problems, we're going to follow the same steps and rules as we did in the previous lesson with regular logs. First thing I'm going to do is combine my two natural logs. We just said that if they're adding, we're multiplying the inside. So that's going to give me natural log of 5x is equal to 1. Now, how do I get rid of the natural log? I make that the exponent of its base. The base is e. So e to the power of ln cancels itself out. I can do this because whatever I do to one side, I do to the other. That gives me 5x is equal to e to the power of 1. Now, when you use e in your calculator, you will always have to put a number in the exponent. So if it's e to the power of 1, that means you're going to have to still put the 1 in your calculator. Then I need to solve for x. Well, what's happening is being multiplied by 5. The opposite of multiplying is dividing. I divide both sides by 5. That gives me x is equal to e to the power of 1 divided by 5. If they're asking for an exact answer, that's what you would write as an exact answer. Now, if they want the approximate value, x is approximately, now we plug that into our calculator. And when we plug that into the calculator, we get 0.5436, and it keeps going. We'll run it at this thousandths, and that gives me x is approximately equal to 0.54. Now here they want the exact value, which is nice. That means we don't have to plug it into a calculator. but we do need to simplify this one. The first thing I want to do is get rid of that radical sign. What I'm going to do is put that into fractional exponents. So remember, if I have the square root of x, that's the same thing as saying x to the power of 1/2. If I have the cubed root of x, that means I have x to the 1/3. And you see where we're going with this. So now the natural log of 5th root of e. First thing we're going to do is change it to fractional exponents. We have the natural log of e to the power of 1/5. We have the property that says I can bring the exponent with a log in front of the log. That's going to give me 1/5 in front, natural log of e. We already said that the natural log of e cancels itself out, leaving me with a final answer of 1/5. This would be an exact answer. We didn't need a calculator. Here they want both the exact answer and the 4 decimal approximation. It's already set up nicely for us, so all we have to do is take the e of both sides. I say e to the power of and e to the power of. On the left-hand side, the natural log and the e cancel out, leaving me with 3x minus 5 is equal to e to the power of 1.1. At this point, we're just solving for x. The opposite of subtracting 5 is to add 5, and the opposite of multiplying by 3 is to divide by 3. Now this is a commonly missed step right here. Remember, the 3 is under the entire thing. Now if you don't like the division of the whole thing, that's perfectly fine. Another way of writing this would be, instead of dividing by 3, I could have simply multiplied by 1/3. So dividing by 3 and multiplying by 1/3 are the same. And what that would look like is, now what I want you to see is that these two answers are the same thing. 1/3 times this whole thing, or the whole thing divided by 3. They mean the same exact thing, and depending on your calculator, one will be easier to plug in than the other. Now, personally, I like the top one better. It looks a little bit nicer, and that's more what we're used to, so that's what we're going to keep. Now, that would be the exact value. The approximate value is the one that you plug into your calculator. So you take that and you plug it into your calculator. And the approximate value comes out to be x is approximately 2.66806. They wanted 4 decimal places. The 6 is going to round the 0 up to a 1. So I'm left with 2.6681. Now we used the e to get rid of the natural log to solve the natural log equations. Now we're using natural log to get rid of the e's for these exponential equations. So the same rules as solving exponential equations last time. We simply take the log of both sides. In this case, it's the natural log. We know that the natural log of e cancels itself out, leaving me with 2x. And whatever you do to one side, you do to the other. So I'm taking the natural log of 17. At this point, the opposite of multiplying by 2 is to divide by 2. So I divide both sides by 2. And then plug it into the calculator. So this is your exact value right there, and your approximate value will be 1.4166. Here's one that looks a little more difficult, but in the end it's pretty much the same. First thing you want to do is isolate that e, get the e by itself. So instead of simply starting with a log, we're going to start by subtracting the 5 from both sides, giving me 3e to the negative 2x is equal to 18. Now we can divide both sides by 3. Leaves me e to the power of negative 2x is equal to 6. At this point, I can take the natural log to cancel out the e, which gives me negative 2x is equal to natural log of 6, and then divide both sides by negative 2, which gives me x is equal to negative natural log of 6 over 2. Remember, I brought that negative sign up because we never leave a negative in the denominator. This would be your exact value. If they want the approximate value, I get an answer of x is approximately equal to 89.59 with a negative sign in front of it. All right, now some application problems. They say, what is the total amount for an investment of $1,000 at 5% for 10 years, compounded continuously? Now this is the most important part at the beginning because it tells you which equation to use. So we know that we're going to use PERT. Now they want the total amount invested, which is your final amount. So remember, the A is your final amount. So we're left with A is equal to, they told us an initial amount of $1,000, and that's going to be our principal. They told us that our rate is 5%. Remember to move the decimal point 2 places. 5% is the same as 0.05. So we're going to have e to the power of 0.05. And then our time is 10 years. So we put a 10 for time at the top. At this point, you just do the basic math. 0.05 times 10 raised as a power of e. Plug it into your calculator, and you're left with a number of 1,648.72. Remember, it is money, so we'll always round to 2 decimal points. Here's another PERT problem. It says what is the total amount of money invested when it's compounded continuously. So we use PERT. $500 is our initial. They want to know our final amount. So the amount is equal to our principal of $500, e to the power of 5.25%. Don't forget to move your decimal place twice. 0.0525 times our time, which was 40 years. Simply plug it in your calculator, which gives you a dollar amount of $4,083.08. Here's a half-life problem. We know the formula for half-life is N of t is equal to N naught. That means your initial amount, e to the power of negative kt, where t is time, and k is the decay constant. This is a paleontologist uncovers a fossil of a saber-toothed tiger in California. He analyzes the fossil and concludes that the specimen contains 15% of its original carbon. Carbon-14 has a half-life of 5,730 years. Use the carbon-14 dating to determine the age of the fossil. Now, problem is we have too many variables. I need to determine the age of the fossil, which is time, but I need the k. I need the decay constant. So what I can do is figure out what the decay constant for carbon-14 is first using the information that I have. We know that the half-life is 5,730 years. So I'm going to use this for my first time. We don't know what k is, but the time is 5,730 years. Now, we don't know an initial and final amount. It's easy. Make your initial amount 1. There's a whole specimen, 1 whole specimen. Now, we're not using the 15% yet because we're still solving for the k first, and this is a half-life. They tell us right here, half-life 5,730 years. Since I used the 5,730, that means I'm finding half-life, so we're going to have 1/2. If we started with 1 in a half-life, you're going to have 1/2. Now you just solve it, just that simple. Take the natural log of both sides, leaving you with natural log of 1/2 is equal to, and the 1 we can ignore, the natural log of e cancels out, leaving you with negative k times 5730. Now we can divide both sides by 5730. The negatives are going to cancel out. The 5730s are going to cancel out. And that gives me k is equal to 0.000121. And that's as many numbers as I'm going to write down. But in reality, it would be 1209680, etc., etc., and keeps going on forever. If you can, use the number that's saved in your calculator. That number should be saved in your calculator. Use it so there's no rounding error. Now that I have the k value, I'm going to use the k value to find the actual age of my fossil. So we start this over again. For the fossil that I'm using, I'm going to do the same thing with the initial amount. I'm going to use 1. They said that 15% is left when we found the tiger. So the final amount is going to be 0.15. E to the negative, the k value we just figured out. That's 0.000121. And then time is what we're solving for. So you do all the same steps again. This time we're solving for time. In order to get rid of the e, I'm going to take the natural log. Natural log and e cancels out. That leaves me with natural log of 0.15 is equal to negative 0.00. Now I can divide both sides by the negative 0.00121. And then I plug it into the calculator. Now when I plug in the calculator, I'm not using 1-to-1. I'm going to use the actual number in the calculator. So I'm going to type in natural log of 0.15 divided by, and what I'm going to do in the calculator is I'm just going to pull the number from the previous answer. I'm just going to pull that number that's saved in the memory. And that gives me an answer of 15,682.8 years. Now, for argument's sake, if instead of using the number from the memory, and I simply used the 0.00121, that would give me a slightly different number, and that's called a rounding error. So the rounding error number would be 15,678.7. Now, which number is best? Obviously, the pink number here is the very best answer. However, if you'd only used the 121, then you'd get the 15,678.7. When doing these for your homework, they'll usually tell you which number to use.